Today, we want to do some examples wherein we think about integration. Remember how integration works, the things that we want to think about when we're thinking about integration. Integration is multiplication, but one of the factors is variable. Integration is multiplication, but one of the factors is variable. So this is where we're going to start getting our applications. What this means for us is that anytime we have a multiplication, we can turn that into integration problems. So what we're going to do with this means we're going to turn multiplication problems into integration problems. So here's how we're going to turn multiplication problems into integration problems. So that's why I want to think of integration as multiplication, but one of the factors is variable. Number two thing, we want to remember that multiplication is repeated addition. Multiplication is repeated addition. It's what we do when all the terms in our addition are the same. So multiplication is repeated addition. We use multiplication when all the terms are the same. We use multiplication when all the terms are the same. But we're going to have to, but what we're going to see is in this bullet point right here, multiplication, but one of the factors is variable. So what this means is that since integration is multiplication, but one of the factors is variable, we have to drop our multiplication back down to addition. We don't get to advance go up one level in the order of operations. We have to stay at the addition level. So integration is addition. And when we're thinking of the addition, we're thinking of accumulation is another way to think about it. But I use addition But when you start looking around the internet and looking for integration is addition, it might come up more often if you use accumulation. So think about the Riemann sum. So one of the ways we develop integration is the Riemann sum. And then the big change, the thing that calculus brings to the table, in this integration process is that since we're doing addition, we don't want in addition, instead of having discrete terms, we're going to have a continuous sum. We're going to be adding up not a discrete sum, but a continuous sum. So we're doing addition over a continuous, we're going to have a continuous sum. Someday I'm going to make this sentence happen. I don't know, it might not be today, but one day that sentence might happen. And this is what calculus brings to the table. Limits is the main thing. This is what calculus brings to the table. So when we're thinking about a Riemann sum, we're just evaluating the function at a bunch of points and using that value for a small change in x. Because if the change in x is small enough, the function isn't going to change that much so long as it's continuous. But this is still a discrete sum. This is f at x1, f at x2, f at x3, and up to f at xn. The calculus part shows up when we take the limit as n goes to infinity. So calculus happens in this part. That's the calculus part. We start off with the f at xi delta x part. This is a discrete sum. Because it has individual terms, and we can separate them and we can count them. F at x1, f at x2, and so on up to f at xn. It's n terms, and we can count them. But taking the limit as n goes to infinity, that's taking our discrete sum, and now we're not adding up values of the function, a discrete number of values of the function. Now we're adding up continuously the values of the function. That's the big idea. This is what calculus is mostly about. A lot of times we talk about calculus as being the mathematics of change, which is fine. But really what we care about is the mathematics of instantaneous change. It's the mathematics where we start studying infinity. So all the math that you've had up to this point has been learning the language, and calculus is where we really start going after what we mean when we say infinity. What do we mean rigorously when we say infinity? Because it's just been kind of this nebulous concept before. And now that calculus has hit the scene, we rigorously define what we're talking about when we talk about infinity. And that means defining things like limits. So this is the thinking that is sitting behind our integration problems. And notice that this sits completely separate from any kind of technique, and takes us all the way back to just your core operations: addition, multiplication, and, well, eventually exponents. So the multiplication part is right here in f at xi times delta x. Here's our multiplication. So there's the multiplication from the first bullet point. Integration is multiplication, but one of the factors is variable. The other way we want to think about this is that if everything is constant, then we get to multiply. But if one of our factors is variable, then we have to integrate. We have to switch over to integrate. When we switch over to integrating, that just means we're going to drop back from multiplication to addition. Since our function is changing continuously, we just pick a value of the function to use for a little while. That's what's going on in this multiplication right here. F at xi is us picking a value for the function to use for a little while. F at xi is a value of the function that we're going to use for the delta x. So what we're doing here is we choose a value of the function. since we want our multiplication problems to be where we want everything to be constant in our multiplication problems, because that's when we get to multiply. So we just kind of make that happen. We say, instead of f continuously changing for this delta x, I'm going to say it's this value, f at xi, and I'm just going to multiply, because if I assume that f is constant for some small delta x, I get to multiply. Then what we'll do is we'll just do that more often. We add everything up, and then we just do the break it down into pieces more often. Any questions? I'm in trouble forming sentences today. I don't know if it's a more coffee problem or a less coffee problem, but I know what solution I'm going to attempt. All right. As an example, or before we get to the example, the tricky part is going to be looking at a scenario where there's just some multiplication going on and figuring out what function we should integrate. So the whole problem is about figuring out what integral we want to set up. A lot of times in math class, you'll hear people say things like, well, once the problem is set up, then I can do the problem. But I have difficulty in setting the problem up. That is exactly having difficulty in math. The whole point of the math class is to get your mechanics down so you don't have to think about your mechanics. So you don't have to do the mechanics that you had, that you've been learning about. You want to skip over all that and get to the real part of the mathematics, which is setting things up. The whole point is to be able to set up problems, to describe things in a mathematical language. Then you can use the tools that you don't have to think about anymore. That's the goal of the math class. It's not about factoring polynomials. It's about what factoring polynomials represents. I always pick on factoring polynomials. Factoring polynomials always feels very called out in my class. So let's do, I don't know if it'll fit here. I'm going to make it try. I'm going to try to. Let's do a classic problem. We're going to draw. Let's see, there's a space. Center. I should have had a nice circle ready to go, but I mean, if you had a professional teacher, then that's what would have happened, but you got me, so tough. I never take into account the width of the pen. There we go. All right. This is my super cool drawing compass. It's the Iris. Hang on. I don't know if I've featured this in class before, but it's called the Iris drawing compass. So I saw it on Kickstarter, and then yeah, here's the information. Not sponsored by this, not sponsored by Maker's Cabinet, but if you draw circles a lot, then go check out Maker's Cabinet. They have a lot of cool stuff. So not sponsored or anything like that. I'm just a fan of their work. I mean, especially because like the little centering thing acts as a stand too. So I got like a little choppa eye on my desk because I can like change the thing. That's a reference that not many people are going to get, but It doesn't close all the way like a Stargate, but that's okay. Still, very cool little tool. All right, so what we're going to do is a classic problem in math that shows up in calculus, and this is going to be a point where we use way too much math to solve a problem to which we already have the answer, because that's a fun activity. So for example, let's find the area of a circle, but let's use too much math to do it. We're going to find the area of a circle with a radius of r. So let's draw a circle with a radius of r. Now, the nice thing is we already know what the area is. So we're going to use too much math to do it. So we want to use an excessive amount of math. The point is not pi r squared. The point is arriving at pi r squared and seeing that when we want to calculate area, the only area is length times width. The only area we need is length times width. So here's what we're going to do. I'm going to draw a diameter of the circle. Just going to mark a diameter of the circle so that we can remind ourselves that this is a circle of radius r. So the distance from the center, what side do I want to put it on? Maybe this side. To the bottom. That's going to be a distance of r. That's the radius of the circle. So we're calculating an area, and area is length times width. That's the only area we need. Area is equal to length times width. That's going to be the area of a rectangle. So area is length times width. What we're going to do is we're going to think of this circle as a bunch of rectangles. Because if the rectangles are small enough, we can fool our eyes into thinking that there is a circle there, just like our computer monitors do. So like computer graphics, I don't know where computer graphics are right now, but it's just a bunch of pixels that are either on or off or different colors. And it's using so many little straight lines that we think we're looking at curvy bits, but it's not. So we're saying, hey, computer, draw a circle. And then it produces a circle for us. And we're like, oh, wow, that's a nice circle. And meanwhile, the computer's like, oh, this dummy thinks I'm drawing a circle. I just drew a bunch of dots. So we're going to do the same thing. We're going to drop the resolution down to like Atari 2600. That went too far. Drop it down to Game Boy. I don't know if anybody knows what a Game Boy is. Drop it down to the graphics. I need not graphics from the 90s. Something from the 90s that has terrible graphics. Aha! I'm going to drop it down to graphing calculator level of resolution, where we can see the individual pixels. So I don't know. Does anybody know what an Atari 2600 is? This is also the old person test, or the super nerdy gamer test. So like if you were born in the 90s and you like still are like, oh yeah, I'm familiar with the Atari 2600, or even crazier, VCS, before they called it the Atari 2600. Yeah, that's classic. I still have an operating Atari 2600. I don't have a Heavy 6. It's one of it's like the second generation, still the same stuff, but the box design is different. So, but it still works. I need to fix one of the joysticks. But video game history. That's your video game history for today. So what we're going to do is the only area that we have is length times width. It's multiplication. The problem that we come into is that one of these, length or the width, is going to be variable as we go around the circle. So notice that if I pick a line right here, higher up, if I cut the circle right here, if I want to do length times width, so if this is let's call this the width. If this is the width, then the length is going to be changing because the circle is going to be cutting in. I'm not going to be able to fit a rectangle. So what we're going to do is fit it anyway. So what we're going to do is we're going to take this width. We're going to assume that the width is constant for some small change. So this is what we're going to draw. I'm going to put a little headband on our circle. So here we are doing exactly what we always do in calculus. We want to calculate with multiplication, length times width, but the length is not constant over the width. So we assume the length is constant for a small change in the width so that we can use multiplication. So I'm going to have to pick which one is which. So I'm going to say this is the width. I can't remember. I think I said this was the width before. And then this is the length. So the width keeps changing because we start off with the diameter. The width is the diameter down here. Then we get to the top of the circle and the width is dropped down to 0. The width is variable, so we don't get to multiply. So we force the issue. We make the width constant for some small change in the length, and that's where this rectangle comes from. Assume that the width is constant for some small change in the length. Assume width is constant for some small change in length. The reason that we're doing this is because we want to multiply. I want to say area is length times width, but the stupid width keeps changing. Goes from the diameter of the circle down here to the 2r down here up to 0 at the top of the circle. So the width is variable. So what we're going to do is we're going to slice the circle up into a bunch of rectangles. Now when I look at this picture, I see South Park Canadians wearing headbands. So it's like Karate Kid, but with Canadians from South Park. And now I can't unsee it. I'm not your buddy, guy. So what we have to do is write an expression for the width and then come up with a variable. Any questions on why this setup fits with the description we had before? I want to say area is equal to length times width. I'm going to but the width keeps changing. So I'm going to divide the circle into a bunch of horizontal strips. And I'm going to assume that the width is constant for some small change in the length. That means we get to multiply, and then I'll just drop it back to addition and add up all the rectangles. So we multiply to get the area of the rectangle, then add up all the rectangles. Then calculus shows up and says, make the rectangles infinitely thin so that you have infinitely many of them. Right. So let's assign some variables. The way that this is going to work is that I'm going to say, I'm going to come up with an expression for W based on where we are in the circle. We know that area is equal to length times width. This is our basic multiplication. Area is equal to length times width. And my plan is to write an expression for the width based on where we are in the circle. So we're going to write an expression for the width. Write an expression for the width based on where that strip is in the circle. So down over here at the rectangle that sits at the diameter of the circle will have a width of 2r. And then it needs to shrink until we get to the top of the circle where the width is going to be 0. But notice that it's not doing it linearly. Otherwise, I just have a square, and that would be easier to calculate. But this is the thing that we need to do. Area is equal to length times width. I'm going to assume that the width is constant for some small change in the length. So now I need to write an expression for the width based on where we are in the circle. So here's how we're going to measure where we are in the circle. I'm going to say that this generic strip is X units from the center of the circle. So I'm going to define my variable to be up in here. So this is going to be where, this is us identifying where we are in the circle. So let X be the distance from the center of the circle to the strip. L is going to be some small change in that variable. So now I can get to call L delta X. So L is going to be some small change in X. We have to write an expression for the width based on where we are in the circle. So now we have to map out the circle so we can identify where we are in the circle. And here's how we're going to do it. Our location in the circle will be the distance from a horizontal strip to the center of the circle. Now what we need to do is somehow write W in terms of X. There's no trick to it. It's just a simple trick. What we're going to leverage is what we know about the circle, and that the circle has a radius of r. So this distance is r. No matter where that strip is, it's got one corner on the circle, And so we'll always be able to make this right triangle with a hypotenuse that's equal to the radius. So here, this right triangle is how we're going to get a relationship between this vertical distance x and this horizontal quantity w. We've now established a relationship between x, w, and r. I just realized I forgot something. I didn't finish my roadmap. How did you guys let me get away with that? So we need to write an expression for the width based on where we are in the circle. I've decided that where we are in the circle will be the distance from the center of the circle to the slice. So this is what we're going to call x. I forgot that once we decide what x is, we have to finish making our roadmap, but I didn't finish making our roadmap. What this means is that this horizontal strip is going to be x units from the center of the circle. When I've drawn x this way, I've decided where 0 is going to be. Once we define the x, that tells us where 0 is going to be. So 0 is here at the center of the circle. That's part of our roadmap. Because a horizontal strip that sits on this, goes through the center of the circle will be 0 units away from the center of the circle. So that tells us the value of x at the top of the circle and the value of x at the bottom of the circle. Any questions? This seems like a lot of work to end up at pi r squared, but pi r squared is not the point. Any questions? I also know that I keep backing up and reviewing the things. And for the most part, you're just kind of like, at this point, you're like hate watching the show. You're like, I just want to find out what happens. It's like The Walking Dead past season 5. It's like, I just want to find out what happens. Or like season 8 of Game of Thrones. You just kind of want it to be over. You're tired of this and you want it to be over. But I keep going back and reminding you of all the plot points. So now I'm going to pull out that right triangle and we're going to see a relationship between w and x. That will be what we're looking for, an expression for the width based on where we are in the circle. I had to define what my variable is. So I had to figure out where 0 is going to be. That's going to tell me where that's going to tell me what values of x define the circle. And that will be how we define our expression for based on where we are in the circle. So we have to be able to describe where we are in the circle. All right. So now let's pull out that right triangle. Let's pull out the right triangle and look at all the parts. It's got a hypotenuse, that's the radius. X is the distance from, here's the center of the circle. And so X is this vertical leg. And this horizontal leg is half of the width of this rectangle. So it's going to be W over 2. And so now we have a relationship between W and X. The width in terms of X will be 2 times the square roots of r squared minus x squared. So now I've written the width. I have an expression for the width in terms of where we are in the circle. It's going to be 2 times the square root of r squared minus x squared. I just use a Pythagorean theorem. So I have the square of the quotient of Wn2 plus x squared equals r squared. Now I can write an expression for the area of that rectangular strip. It's going to be 2 square roots of r squared minus x squared. That's the width, multiplied by the length, which is some small change in x, so delta x. Now we just need to integrate that over all the values of x for which console strip. So I wanted to do area is equal to length times width. And I just wrote an expression for the width of the slice. So I should make a note of this. This is the area of the slice. So the width is 2 times the square roots of r squared minus x squared, and the length is delta x. Now I have the area of each slice in terms of the variable x. Then we just need to make a Riemann sum. So what we're going to do now is add up all such slices. So we start off by breaking it up into n slices, so r squared minus xi squared times delta x. And then we drop the calculus bomb on it. We take the limit as n goes to infinity. Calculus has entered the chat. This turns our Riemann sum into a definite integral, which is the thing that we were really going for. So we're going to integrate 2 times the square root of r squared minus x squared. Notice that the xi is the discrete values of x. That's where we have a list of x's. And we have this discrete width delta x, or this small positive width delta x. But now we're in a continuous sum because we're looking at an integral. So xi just becomes the continuous x, and the continuous form of delta x is the dx. The last thing that we need to turn this into a definite integral is we need to integrate where there are slices. Integrate the values of x for which there is a slice. Now we need to make the definite integral where we integrate where we have a slice. So looking at our diagram, the values of x that tell us where the circle is are from negative r to r. So those are all the values of x for which that'll represent a slice. So we'll integrate from negative r to r. So here's a definite integral that should give us the area of the circle. We can try this for some fixed value of r. Let's try that. Let's see if this, whoops, let me show you that. Let's pick r equals 5. That'll do. So let's do an integral. Let's do an f(n) integral from 2 times the square root of 5 squared minus x squared with respect to x from -5 to 5. Divide that by pi and we get 25, exactly what we expected. The little bit of the little 15 at the end, that's because we rounded things off. We're approximating things. If we tried another one, let's see. Let's change 5 to 3. And let's just go ahead and divide. Oh, we get eventually 28.27. And if we divide the pi out, we see that this is 9 pi, exactly what we expected. Any questions? It's because it's after 9 o'clock that I just grabbed a couple of examples. But what would have to happen now is that we would try to integrate this function. To integrate this function, notice that we have the square root of r squared minus x squared. So the integration would be a trigonometric substitution. So the integral, definite integral. We'd have to do a trigonometric substitution. It looks like x is going to be r sine theta. And then that would get us to pi r squared. This seems like a lot of work to come up with pi r squared, something that we already know. But it's important to take a new process and apply it to things that you already know to make sure that your process is going to work. And the point is not coming up with pi r squared. The point is coming up with the process, so that when it's not something that's familiar, we have a process that gets around it. And we can say, can we just divide this up into a bunch of rectangles? Because all we need for area is length times width. All right, that's going to do it for today. That's going to do it for this week. I'll see y'all on Monday. Everybody have a nice weekend, and thanks for playing.